This is how the emission of a hydrogen alpha photon, caused by an energy level transition of the hydrogen's electron, is normally shown. The electron makes a magic quantum jump from level n equals 3 to level n equals 2, and the photon comes out at the speed of light. But quantum mechanics says that combinations, or superpositions, of the n equals 2 and n equals 3 solutions are also valid solutions in themselves. We can interpret the theory in a way that these superpositions play a role in the transition, which enable us to see it instead as a continuous process. In this animation we will be looking at two-dimensional representations of the electron wave function, which must satisfy the Schrödinger wave equation. This is a complex value with a phase angle and an amplitude at every point in space-time, and we will show the phase as a hue on the color wheel. We'll represent the intensity, or amplitude squared, as the intensity of the color, from 0 up to its maximum value. When we want to show the intensity without the phase, we'll gray out the color. Here is a freeze frame of the solution for the n equals 2 orbital. This orbital has a distribution that lies in a donut shape around the nucleus of the atom, with a phase that cycles through all the values or colors as you move around the ring. When we turn on the time dependence to see how the wave moves, what we are seeing is that the phase at each point in space is cycling through all of the colors, but to our eyes it looks like the whole orbital is rotating around the center. We have arbitrarily chosen to make the frequency of this 2 cycles per second. The n equals 3 orbital is bigger, as you can see, but this solution has a phase that cycles twice as you go around the center, so we get 2 copies of the rainbow of colors. Now, we'll set this one in motion, but this time at a higher frequency of 3 cycles per second corresponding to the higher energy. Though the colors are cycling 3 times per second at each point, to our eyes that looks like 2 copies of the rainbow rotating at 1.5 times per second. The important thing about these orbitals is that only the phase varies in time. Hiding the phase, we see that the intensity is constant, which is why they are called stationary states. In this model we will consider the intensity distribution as an actual distribution of the electron's charge, rather than the traditional interpretation as a probability distribution. Since the charge is not moving, and it shares a common center with the opposite charge of the nucleus, it does not generate any electromagnetic field or radiate any energy, as shown by the flatness of the red line representing the electromagnetic field excitation. It is metastable. It will remain in this condition until it is disturbed. But any external influence, such as electromagnetic radiation from outside, will cause the pure n equals 3 solution to no longer be valid, and the electron will need to shift into a superposition state, in this case, a mixture of mostly n equals 3 with a tiny bit of the n equals 2 orbital mixed in. As this happens, the previously stationary distribution begins to wobble. The interaction of the phase component at the 2 different frequencies causes this motion, and its frequency is the difference between the frequencies of the 2 orbitals, like a beat tone between 2 musical notes, at 1 cycle per second. As the energy begins to be carried away, it takes the wave function farther and farther from the n equals 3 solution and more towards the lower energy n equals 2 solution. When this process is about half complete, the wobble is at its maximum and the electromagnetic excitation is greatest. The central peak of a wave packet is generated, and the electron begins to settle into the n equals 2 orbital. This is the creation of a hydrogen alpha photon. The beauty of this is that, for both the electron and for the electromagnetic field, this frequency is directly proportional to the energy, with Planck's constant as the proportionality constant. The transitioning electron excites the electromagnetic field at exactly the frequency that the photon needs to be, to carry away the energy difference between the n equals 3 and n equals 2 orbitals. Of course, the reverse process can also occur, in which an incoming photon would begin to excite the electron into an upward superposition between its starting state and a higher level, after which the electromagnetic waves would resonate with the oscillation of the intensity distribution until the electron is pumped upward into the higher, metastable state, and an entire photon is absorbed in the process.